Good morning, physics students. Here is your concept development practice page 10.1 about acceleration and circular motion. Newton's second law, A equals force divided by mass, right, and net force, tells us that net force and its corresponding acceleration are always in the same direction. Both force and acceleration are vector quantities. But force and acceleration are not always in the same direction, or in the direction of velocity, which is another vector. So, number one, you're in a car at a traffic light. The light turns green and the driver steps on the gas. Your body lurches, right? So your body moves backwards when you suddenly start moving. The car accelerates forward. The force on the car acts forward. The sketch shows the top view of the car. Note the directions of the velocity and acceleration vectors. So our velocity is forward and our acceleration is forward as well. Again, our velocity is forward because we are increasing our speed. Or actually, our velocity, that's not quite the best way to describe that. Our velocity is forward because we're moving forward. And our acceleration is forward because we're increasing our speed. And remember, acceleration, another way to define acceleration is it's our change in velocity over our change in time. So number two, you are driving along and approach a stop sign. The driver steps on the brakes. Your body lurches, right? So you kind of move forward until your seatbelt stops you. Okay. The car accelerates. So this time, because the car is decelerating, right? The car really is accelerating, we can say backward, and that's because the car is decelerating. Okay, so if we wanted to draw our acceleration vector, it would be towards the back. The force on the car acts, again, we're talking about force here, right? And the force would be acting backward because net force and acceleration are in the same direction, right? Tells us that net force and its corresponding acceleration are always in the same direction. So if our acceleration is this way, then our net force also, okay, has to be backwards as well. So the sketch shows the top view of the car. Draw vectors for velocity and acceleration. So our velocity vector, the car is still moving forward, right? So our velocity vector, okay, is still to the front because the car is still moving forward. It's just slowing down its movement forward. Okay, this acceleration is backwards because it's decreasing its speed. So, number three, you continue driving and round a sharp curve to the left at constant speed. Your body leans, you lean outward, right? Kind of against your door. The direction of the car's acceleration is, okay, inward. And again, the deal being here, we're at constant speed, so what's causing our acceleration? Our acceleration is due to the change in direction. The force on the car then has to act inward because, again, net force and acceleration are always in the same direction. So we draw our vectors. That means our acceleration, okay, is toward the inner part of the curve, but our velocity, again, our car is still moving forward, so our velocity still is moving forward. So this is because it's moving forward. And this is because it's in a curve. And again, when we're in our curve, our acceleration is towards the center of that curve. In general, the directions of lurch and acceleration. So what it's asking is, here our lurch is outward, our acceleration's inward. Lurch is forward, our acceleration's backward. Lurch is backward, our acceleration is forward. Okay? In general, the directions of lurch and acceleration, and therefore the directions of lurch and force, are, okay, and they're usually opposite. And again, why do we say force? Because remember, our net force is the same direction as our acceleration. The whirling stone's direction of motion keeps changing. If it moves faster, its direction changes faster, right? This indicates that as speed increases, acceleration increases. Consider whirling the stone on a shorter string, that is, of smaller radius. For a given speed, the rate that the stone changes direction is going to be more, right? It's going to move around its circular path more quickly. This indicates that as the radius decreases, acceleration also increases. So looking at centripetal force, a rock tied to a post moves in a circle at constant speed on a frictionless horizontal surface. All the forces acting on the rock are shown. Tension T, okay, so that's in the string. Support force N, which is the table, okay, and by the table, and the force due to gravity W. Letter A, the vector responsible for the circular motion. So which one of these is causing the circular motion? Well, that's that tension vector. The net force on the rock, right? If I'm causing circular motion, then the net force on that has to be T. And we can kind of tell that because notice in our picture, our three force vectors are here, and weight and the support force are equal in size and opposite in direction, which means they cross out. That means the only force left on that rock is that tension of the string. In this case, the rock is tied to a string and swings in a circular path as shown. It is not resting on a surface, so there is no friction. Use the parallelogram rule and find the resultant of vectors T and W. So what this is asking us to do is, like we have done previously, is to make this a parallelogram. So remember, we draw two parallel lines. And then remember, our resultant goes from where the two of them meet to where the other ones meet. Okay, so there's our resultant. Okay. So, letter A, what is the direction of the resultant of T and W, right? So this is our resultant. Well, what direction is it? Well, it's toward the center of the circle, right? Because here's that circle, and it's definitely towards the center of that circle. Does this resultant lie in the plane of the circular path? So, is it lie in this plane? Yeah, it does. Is the resultant also the horizontal component of our tension? Right, so remember our tension, there's the horizontal and then there's the vertical component. And yes, it would be the horizontal component of our tension. Is the resultant of tension and weight, or the horizontal component of tension, a centripetal force? Yes, because it's directed towards the center of a circle. Number 3, in the case shown at the right, the rock rides on a horizontal disc that rotates at constant speed about its vertical axis, a dotted line. Friction prevents the rock from sliding. Draw and label vectors for all forces that act on the rock. So again, we have certainly, right, the pull of gravity acting on this, and that would be acting downward. So that's our pull of gravity, which is our weight. We also have, right, the support force of the table acting upwards. That we've been calling N, right? That's our normal force or our support force. And because our rock is not falling or rising vertically, we know that these, the support force and the weight, have to be equal in size and opposite in direction. Now, we also know there's another force at act here, okay? And that would be a force that's directed towards the center of this circle. Okay, so we'll just call it a force. Call it F. So which force is centripetal? Which force is directed towards the middle of a circle? Well, F. Okay. Which force provides the net force? Again, these are equal in size and opposite in direction, which means they add up to 0. So the only net force on this is that force F directed towards the middle of our circle. Why do we not say that that force is 0? Okay. Because there's acceleration, and specifically it's centripetal acceleration toward the middle of that circle. So the net force can't be 0. Because again, to have acceleration, there must be a net force acting on the object. Now the rock is held in place by friction against the inside wall of the rotating drum. Draw and label vectors for all forces that act on the rock. Again, we know that there's gravity acting on it downwards. So that's our weight. Now, there's a support force this time, right, from the edge of this drum, but our support forces always act at a 90-degree angle to our surface. So our support force would be acting this way. So again, that's our N, our support force. Now, this ball is not moving up or down, so there's a friction force acting upwards. So this is friction force. Okay, so those are our forces. So which force is centripetal? Which one is acting towards the middle of our circle? Our force N. Which force provides the net force? Again, our friction force and our weight are equal in size and opposite in direction. So which one provides our net force? Our N does. More challenging, this time the rock is resting against the frictionless inside wall of a cone. It moves with the cone, which rotates about its vertical axis. The rock does not slide up or down in the cone as it rotates. Draw and label vectors for all forces that act on this. Again, this is kind of like extra credit, if you will, right? So we certainly have the weight acting downward. And that always acts straight down. Now, we also have that support force, right, which acts at a 90-degree angle to the wall. So here's our normal force. Okay. Now, those are our forces. Should the resultant force lie in the plane of a circular path? Well, it should, because there should be centripetal action or centripetal force. So again, to do that, we have to do that parallelogram. So here's my force. And notice it does lie. Okay. And it's because this is a rotation, or well, better to say, because there's circular motion, there's a centripetal force, and centripetal force always has to act towards the center of a circle. So again, the important kind of takeaway is, remember, our net force is always in the direction of our acceleration. Okay. And again, if we whirl a stone faster, we're changing the direction of the motion faster, which means we have more acceleration. And if we shorten the string we're whirling it on, it's going to change its direction faster as well, which means we have an increase in acceleration. And anytime we have a net force directed towards the middle of a circle, we have a centripetal force. So I hope that helps. Have a great day, and I'll talk to you tomorrow.